sphere, but you can imagine it might be distorted, not like that. Now, what is a trapped surface? You have to imagine that there's a flash of light emitted all along that surface. Here. On the top left, you see a picture of a little surface, and you imagine, suppose there's a flash of light occurring on that surface. And if it's convex, well, on the concave side, the flash will be converging. On the convex side, it will be diverging. And that will be the normal thing for a surface. Now, on the top right, you have something which is sort of, you might imagine that it can converge on both sides. On the bottom, you see a much more general situation, which doesn't depend on any kind of curvature. You get this in flat space. The intersection of two past light cones, you get this property of a locally trapped surface. Now, the trouble is that when you have a surface like this, which is global all the way around, such as in the picture that I have on the central ring, which is really a two-surface, and I'm imagining that a flash of light occurring on that, it's converging on both sides. And that's what a trapped surface is. And what I was able to show, that if you have energy which is locally positive, and you look at the behavior of the future of that surface, that you must run into a contradiction. That is to say, you get a singularity. So this was a proof, in general circumstances, that you couldn't have irregularity or something swishing around in a complicated way and come swirling out again. You would always get a singularity. And this was the central theorem that I proved, which eventually seems to have won me the Nobel Prize. Okay, now let's think about the universe as a whole. Now you see, Stephen Hawking was not at that talk, but Dennis Sharma got me to give a repeat talk in Cambridge, and Stephen was at that talk in Cambridge, and we had quite a long chat afterwards about the methods I was using. George Ellis was there also, and Stephen picked up on it very quickly and developed these ideas by generalizing my arguments to apply to a cosmological model. I won't go into the details of this, but the main point was that you could also show, using the arguments that he developed, and also we got together eventually and wrote a paper together, which more or less encompassed the things that we'd done before. And this showed under very general circumstances, in the past now, if you have some kind of diverging ray, some kind of expansion in the universe, then you couldn't avoid having this singular state in the very early universe. Now, this was fine, that you seemed to prove these singularities. But I remember being very puzzled by why cosmologists didn't study all the different kinds of singularity you could have, because they're very common. There are many, many solutions known to general relativists where you could get very complicated singularities. And I remember this was an occasion when I think I was at Princeton, and we were about to go to a conference at Stevens Institute in Hoboken, and we used to drive up in several cars. And I noticed in the car, in the back of one of these cars, was Jim Peebles. This was last year's Nobel Prize winner in physics. This was long before that, of course. But I noticed he was there, and I asked him, I said, why don't you cosmologists ever consider all these complicated possible singularities that you could have, and you just look at this simple case? Why don't you look at these other cases? And he looked at me and says, because the universe is not like that. And I thought, my gosh, it's not, is it? I presume that he was looking at the microwave background radiation, which is very uniform over the whole sky, and it tells you that the universe really is very uniform. So it tells me that there's something very strange about these singularities, that the Big Bang singularity is utterly different from the kinds that you see in the future, in the collapses in black holes. And I was very puzzled by this, and since everybody seemed to think that the solution of the singularity problem was that you had to combine general relativity with quantum mechanics, you had to find a quantum gravity theory. It must be a very peculiar quantum gravity theory, which is grossly asymmetrical in time, which gives you a theory which makes the singularities quite different in the past and the future. Well, I had this view for quite a long time, until I think I started to worry more about, I thought I worried about the singularities in relation to the entropy in the universe. I'll come to that in a minute. But first of all, let me talk about what the universe is actually like according to what people think. You see, what they think is that the Big Bang was not just like this, And if you have a magnifying glass, you can have a good look at it. There's something called inflation. Now, inflation, according to the theory, is another exponential expansion, which took place with a tiny, tiny, tiny fraction, 10 to the minus 30 something or other of a second. And that is supposed to have taken place, this exponential expansion, and it was supposed to have smoothed out the universe and do various other things to do with the microwave background, make it look as though it was scale invariant and things like that. So it had a role to play, but I didn't see that it would smooth out the universe. Well, the reasoning I was using is, suppose that you imagine a collapsing universe. So here we have a collapsing universe. And this collapsing universe, suppose we put the inflaton field, which is supposed to give you inflation. Well, it just doesn't do anything. If you have irregularities, black holes all congealing together, the picture would look more like this, a great mess, with your Weyl curvature diverging like mad. And then you imagine, well, that is much more likely thing, and you can work out how much more likely it is, something like the probability of finding this is 10 to the 10 to the 100 and something, 10 to the power of 120 or something, that you get that more likely than the asymmetrical model that we seem to see, at least in the Big Bang. But in the Big Crunch, if you had the universe collapsing into a mess like this is what you get. But the question is, why wasn't it like this in the past? Is it a very strange kind of quantum gravity theory, which is what I thought for a while. Now, this is connected with another problem, which is the problem of the second law of thermodynamics. Now, let me describe the picture of the second law of thermodynamics. People often talk about a gas in the box. So the top three pictures, on the left-hand side, we see a gas tucked up into the corner in a little box. You open the box, and it spreads out through the big box, if you like. So as the gas spreads out, it gets more and more uniform. The entropy, or the randomness, increases in accordance with the second law. Now that's what you see, the right-hand side of this picture. You see matter which is very, very uniform in the beginning, which would be a maximum entropy state. In fact, the microwave background, where you see it, it looks like a maximum entropy state. So there's something very funny going on. How can it start off at a maximum? But then when you think about gravity, it works the opposite way, because gravity is uniformly attractive. So here I have a picture on the left of a lot of stars running around, and then they turn to clump, and then they finally get black holes, and the entropy goes shooting up enormously by the Bekenstein-Hawking formula, which tells you what the entropy in a black hole is, and it completely and utterly dominates the entropy in the universe. Right now, almost the entire entropy in our current universe is in black holes by an enormous factor. So we see that what's special about the universe is that the gravitational degrees of freedom were not activated somehow. And I tend to postulate just that maybe quantum gravity tells us in some mysterious theory that somehow the Weyl curvature had to be zero in a past singularity, and it could be infinite in a future singularity. Just sort of waving hands around and no theory which tells you that. And I thought that for a long time. But then, after I became persuaded, and I think I want to go back now, look at this picture, that the universe, this was another Nobel Prize, Saul Perlmutter and Schmidt and Rees discovered the distant supernovae stars seem to be accelerating away from us, and I had to be persuaded of that. And when I came around to believe it, I had some wrong reason for disbelieving it. But when I came around to believing it, I thought, gosh, this means this is interesting. It tells you that the future infinity is space-like. Now let's talk about infinity. You see, people think, how do you talk about infinity? Well, now Escher had a very nice way of describing infinity. This is a conformal representation of what's called hyperbolic geometry. Don't worry about the geometry, but the boundary of this represents infinity. Now, it's a conformal picture. That means that angles are preserved, but sizes can be big or small. And the fish, as they get closer to the edge, they don't really realize that they're small. According to them, they're the same size as the ones in the middle. So this is a conformal representation. You can squash or stretch as long as you don't alter the small shapes. And that's conformal geometry. Now, the importance of conformal geometry I'll come to in a minute, but let me think about the light cone again. The space-time structure means not just the light cone. You need to know these little surfaces within it which are the surfaces of equal time from the origin point. So if you have some light rays, these aren't light rays, sorry, you have two massive particles, and I'm having two different ones going at different speeds, going through the central point, and the ticks of a clock, at the top you see a little clocks these, and the clock registers the time as the world line of that particle intersects these various bowl-shaped surfaces. The first tick, the second tick, the first tick. And by the two formulae at the bottom, we have the two most famous formulae of 20th century physics. Einstein's E equals mc squared and Max Planck's E equals h nu. You put the two together and you see that energy and frequency are equivalent from the Planck, and energy and mass are equivalent from Einstein. Put the two together and you get that mass and frequency are equivalent, which tells you that a massive particle is a very perfect clock. So this is where you get the metric structure. But what about light rays? Well, you see the light ray doesn't even hit the surfaces. So light ray doesn't register the passage of time at all. And here we'll forget about the light ray, the light cone or the null cone is itself gives you the structure of space-time. So if you only got null cones and not the scale, then you have a good picture of infinity. And in fact, you can do this, and not only do you have a picture of infinity, but you can stretch out the Big Bang as well. And this is, you see, I was trying to say as a sort of criterion that the Big Bang or initial singularities ought to have vanishing Weyl curvature. My student Paul Todd had a better way of doing it, to say, okay, let's say that it's extendable to something. You see, you could imagine the Escher picture, you could extend the little fish to beyond the bounding circle to something outside. They don't experience that, but you could imagine there was a world continuing beyond infinity. And here I imagine there might be a world continuing beyond infinity, and there might be a world continuing before the Big Bang. Now, does this make physical sense? It makes geometrical sense, but what about physical sense? Well, you see, the remote future is very rarefied, very cold, and the density is very, very low. When you scale things to squash it, to make it a finite boundary, this makes the energies go up and the temperature go up. And if you stretch out the Big Bang, that makes the energy go down and the temperature go down. And you might imagine that physically they are similar. So would they match? That's a possibility. You need the space-like nature of infinity, and that comes from the cosmological constant. The space-like nature of the Big Bang comes about automatically. You also get something more if you do what I'm now going to suggest, which is to imagine not just that you have a finite boundary at the two ends, but you continue. Our Big Bang was the continuation of something before, and our remote future is will continue to something beyond it. Now, does this make physical sense? Which it only really makes physical sense if you've got massless things around. What about the remote future? Well, the main things running around will be photons, and they're massless. So let's say there's something more, you've got mass as well. I have to sort of suggest that the mass does fade out eventually, but let's say it's dominated by the photons. What about the Big Bang? Well, it's the opposite reason. Here, by Einstein's E equals mc squared, you find that the energy in the mass is pretty well completely dominated by the energy in the motion. So the kinetic energy, when the motions get so big, the energy gets so great, then it's almost entirely in the kinetic energy and not in the mass. So you might as well consider that the mass is zero, and the physics relevant to the two ends is the physics of zero massless particles. In fact, in the remote future, the photons, that's Maxwell's equations don't even notice the metric. They are conformally invariant. And in fact, you can consider that you could actually, if you have electromagnetic things or massless things or gravitational wave things, they could get across from one side to the other. So I can imagine that the crossing over from one side to the other makes sense if your physics is sufficiently conformal and you're not worrying too much about the mass. Okay, now I'm going to finish this talk by talking about two classes of observation. The first one was an idea I had about maybe you would see in the previous eon, if it's like ours. I'm calling the different sections the different eons, so if I go back to this picture, our eon is this initial cylinder. It's not really a cylinder. You see at the back there's some curly stuff. It may not close up at the back, so I don't mind whether the universe is closed spatially or open. Now here I have the join from one to the next, and you might imagine light rays getting across. But what else might get across? Well, here, the previous eon, I'm calling all those different, what we previously called the universe was our eon. There was an eon prior to ours, an eon after ours, and so on. Now, the Big Bang of our eon was the remote future of the previous eon. Now, there might have been in that previous eon black holes, supermassive black holes, running into each other. As they run into each other, they would emit gravitational wave signals. These would get through and make a signal that we might observe in our eon. Moreover, if you imagine what the big, really super-duper massive black holes, which ultimately swallow clusters of galaxies, they will be the result of many, many supermassive black hole collisions, and they will be maybe 1, 2, 3, 4, 5, 6, several of them. So you might see not just a signal of one of these, but several of them. Now, what you would expect to see, according to this theory, would be rings in the cosmic microwave background where the temperature is slightly lower variance as you go around, or higher or lower temperature. But my colleague Vahe Gurzidyan, who looked at this, he looked at concentric sets of at least 3 rings of low variance, low temperature variance. And he plotted these things out. And in the next picture I'm going to show you, which is rather remarkable to me, he didn't select these things from the color, which is the temperature. He didn't select it for that at all. He selected it just for the low variance. And these are plotted out in the Planck data, centers of at least three concentric low variance rings. Now, whatever you believe the origin of this signal is, what is very remarkable is the extreme anisotropy of the picture, or inhomogeneity of the apparent universe here. On the lower right, you see a very large collection of red points. Now, in the color coding and in the theory, I won't go into the details here, the red means distant. So these would, according to the theory, be a collection of very distant supermassive black holes clumped together in some super-duper cluster. On the top right, you see a bluish region. That would be closer to us within our past light cone, so you probably could see that, of something which, again, some not quite so big and super-duper, but pretty super-duper. And a little on the lower, slightly lower left, you see something intermediate. The red ones would be distant, according to my theory, the blue ones. But what's remarkable is not just they're clumped together in where you see them, but they're clumped together in the color, which means, according to the theory, in the distance. So if you don't believe my theory, you have to think of another explanation for this, but it's very much at odds with the current view where the inflation is supposed to stretch things out and flatten everything out. Another possible observation of events in the previous eon would be the evaporation of supermassive black holes according to Stephen Hawking's Hawking evaporation, where the entire mass, ultimately, it may take something like 10 to the 100 years or more for a supermassive black hole finally to disappear in form of radiation. Now, this radiation would get through into the next eon. So here I have a picture taken from a paper written by Christoph Meissner, Pavel Nurovsky, Daniel Ann, and myself in the monthly notices of Royal Astronomical Society. And we see the crossover is the lowest horizontal line in the picture, and the vertical line just meeting it is the world line of a supermassive black hole, which finally evaporates right at the crossover almost into the next eon, really squashed up into that little point. It spreads out through 380,000 years until you finally see it when it reaches the last scattering or decoupling surface. And according to the work of James Peeble and his colleagues, you have a good knowledge of what happens in that previous 380,000 years. But what we actually see is the spread of that point to about 8 times the diameter of the moon. So this would be a heated point which is hotter in the middle by about something like 15 times, it could be as much as that, times the background variations in temperature, the normal variations. And we seem to see in both the WMAP and Planck satellite data these points. In the Planck data, we see it with a confidence in something like 99.98% confidence level. So this is a very strong signal that these points are there. Of the 5 strongest points in the Planck data, these are also seen as exactly the same places in the WMAP data. There's another one in WMAP which is seen the same point in the Planck data. So these 6 points, I think, I have pretty great confidence that they are genuine Hawking points. If not, I think somebody else will have to come up with an explanation for this effect and explain how we can have a confidence of the level we seem to see on the basis of some other theory. Thank you very much.
We're going to listen to Reinhard Genzel talk about the amazing story behind the study of the compact object in the galactic center, a 40-year journey. Reinhard Genzel earned his PhD in physics and astronomy from the University of Bonn in 1978. He held a postdoctoral position at the Harvard-Smithsonian Center of Astrophysics, followed by a Miller Fellowship at the University of California in Berkeley, where he became full professor in 1985. In 1986, he was appointed director of the Max Planck Institute for Extraterrestrial Physics in Garching. Reinhard Genzel has been spearheading the high spatial resolution imaging and spectroscopy studies of the motions of stars surrounding the Sagittarius A radio source in the Milky Way center using the European Southern Observatory facilities in Chile. As we are about to hear a fascinating and still evolving story. Professor Genzel, the floor is yours.
Ladies and gentlemen, dear colleagues, it's a great honor and a pleasure to be here and speak to you about the research we have done in trying to establish that in the center of our nearest galaxy, the Milky Way, is an object which is a massive black hole of 4 million solar masses beyond any reasonable doubt. I've called this the 40-year journey. It's been a long time. Many people were involved. Experimental work has been ongoing for these decades to improve the sensitivity, the accuracy of positional measurements, and the precision of data to come where we are now and where we can say with some certainty what I will tell you. Many people have been involved in my own group, people before me, mentors, but also many students and postdocs. I'm very, very glad to have been able to work with such a great crowd of people. And I also would like to emphasize the great work of our team in California who have been competing with us. But in the end, of course, we have come up with the same basic result, which only strengthens the overall believability of the result. Now, over these decades, of course, there were several phases. So I'll give you this talk in 5 phases. First, the motivation, and then 4 phases within the program which I participated in. Now, let's look at the backdrop. Of course, we know that the theory of general relativity is 100 years old. And the mathematical refinements went on for a number of decades, ending in the 60s with the so-called Kerr space-time metric and the work of Penrose on the ergosphere and others. Roger Penrose being the one who is being honored with the prize this year as well. So this theoretical foundation gave us the idea, the perspective, that there are objects which one would call black holes, which basically are not communicating from the insides with the outside, but can have tremendous impact on the gravitational field, the space-time surrounding it, and therefore influence their environment. Now, this was all theory until the 60s, when several things happened. X-ray astronomers started observing very intensely X-ray emitting binary stars, some of which we now believe are stellar black holes. And that's the most important thing for this talk, the quasars were discovered. Initially by radio astronomers, and then optical astronomers discovered that these objects in optical images look like stars. Yet in their spectra, there's evidence that spectral lines, which are in the laboratory very well known, are shifted by such an amount as to make these objects very distant, many hundreds of millions of light years away, such that what looks like a fairly faint star really must be a tremendously luminous object. This one, the first one, has 1,000 times the luminosity of our entire Milky Way, all coming from the central light year or so. Theorists thinking about this then found out that it was basically impossible to explain the radiation produced in these quasars by normal fusion, like in stars. But, and that's the surprising thing, when material spirals into a massive black hole, before the material disappears in the event horizon and therefore is, escapes from our line of from our view, it can release enormous amount of energy due to the gravitational energy lost, and that can be up to 40% mc squared. So, surprisingly, paradoxically, therefore, the model of massive black hole paradigms for the explanation of quasars was invented. But of course, how would you prove that? Prove that in the sense that you cannot only observe phenomena like high energy radiation or these spectacular radio jets of relativistic plasma emanating from many of the quasars. This is indirect evidence for a very energetic object, but not proof in the sense of actually showing that there's a gravitational potential as compact as you would have to have for a massive black hole. So how would you prove that? In a very famous paper in 1971, Linden, Bell, and Rees then proposed that whilst it's impossible to measure effects of gravity in distant quasars, if all galaxies would have central massive black holes, just most of them not very active in terms of accretion, well, then you could use, in particular, also the center of our Milky Way. So that's how our Milky Way center became center stage and evolved from there to a laboratory. So let's take a trip image, which we can now make with modern telescopes, which shows us the innermost region of our Milky Way being a very dense star cluster. This is shown here in the blue region. And in the center of this star cluster, as you will see in a second, radio astronomers found very intense radio emission, in particular a very compact radio source. Surrounding that radio emission, in green here, is gas, very dense neutral gas, as well as ionized gas, the so-called mini-spiral in ionized gas. In fact, that was the first path towards looking whether there is a central mass. Basically, what one does is to look whether this gas is orbiting and look from the velocities what the mass would be. So indeed, a group around Charles Towns at the University of California with his students started looking at this ionized gas streamers here. You here see how the velocities change along this streamer here, and the numbers here give you the mass which would be required if this would be a free-falling, if you like, parabolic or elliptical orbit, and the numbers are 2, 3, 4, 5 millions of solar masses. So that was the first evidence that there was a lot of mass there, more mass than the stars would allow. Then the next stage was the radio source. Many years have been used to refine the measurement on the radio source. On this diagram, where you here have wavelength versus size of the source, you can see the shorter wavelength you go to, the smaller the source becomes. And spectacularly, when you go to the millimeter waves, here's 1 millimeter. The size of the source is 10 micro arc seconds. To give you a feeling, that's about the size of a euro coin on the moon. That's how compact the radio emission is. And in fact, that would be the event horizon size of a 4 million solar mass black hole. So the combination of this mass being large and this size being small was the first evidence in the 1980s that there might be something in the center of our Milky Way. So here on the left side, one could take the various measurements here and see that this mass was between 1 and 4 million solar masses. Not very accurately initially, maybe 50% or so. On the right side, you see, as a function of distance from the center, the mass, and here you see that within about a parsec or so, there seems to be a constant mass. That's an indication for a concentrated central mass, but still at a very large number of event horizon radii, 1 million. But it was the first evidence. How to go from there? Well, you want to go further in, and you want to use indications which are more stable and more easy to interpret than gas, which can be pushed around by forces other than gravity. And these are stars. And so in the 90s, two groups, one in Europe using telescopes in Chile, and one group in California using the Keck telescope, starting using the new developed infrared imaging detectors for the Space Telescope to build cameras which allowed very short exposures. The trick is that when you take a picture in the optical or in the infrared, then of course the Earth's atmosphere will blur the image such that you cannot make a very high precision measurement. To measure the motions of stars in the sky, you want to have very accurate positional measurements over time and see whether they change. So this was the first technique both groups used, the speckle techniques, as you see here. You make short exposures and freeze the motions of the Earth's atmosphere, and then in post-processing, you basically add the images to get about a 5 times improvement in the angular sharpness of the images over what you can do with normal detection. The second technique which had to be developed is to get spectra, because the motions on the sky give you 2 motions, and the Doppler motions along the line of sight, which is the third, you can get through the spectra from lines in the stellar spectra. For that, we developed what is now called the integral field unit. Basically, a normal spectrometer just disperses the light in one direction and doesn't allow you to image. But by using an image slicer, you can basically generate a huge long slit which decodes the 2 dimensions, and then you bring this through a spectrograph which disperses the light. And then in the end, in the computer, you can put that back together. So using these techniques, a few years later, we had sharp images of the central light years, and we could look for changes on the sky of their positions. Here's an example. The green cross is the position of Sagittarius A star, that radio source, which is so compact. This is 1 light month, this circle, and you can see from time to time to time, from 1 year to the next, in 3 different colors, the position of this star, very near Sagittarius A star, clearly changes. If you look up, then that's a motion of in excess of 1,000 kilometers per second, something which you see not in the solar system. So these stars are whizzing around at a speed of more than 100 times the Earth around the sun. So that's already a qualitative indication of a strong mass. And is it a point mass? Well, okay, Kepler's laws tell you that if you have a central mass and objects are moving around it, and the further away you are, the slower. And indeed, when you look here, the innermost stars move obviously very fast, while the other ones here, do not show this prism effect. So that's Kepler's laws in color, so to speak. And indeed, when you make this more quantitatively, you can derive then the mean speed of the stars as a function of distance from the radio source. That's what this is. And this tail here is indeed the first quantitative indication that indeed there is a 4 million solar mass or 3 million solar mass object in the center, and further out when this flattens, that is the effect of the star cluster surrounding it. So that was the second phase. That was until 98, with stellar motions making more precise estimates of the stellar mass. Now you see we are, at the level of about a little over 10%, and a factor of 5 or so inwards. So it's both a more precise measurement of the mass, as well as concentrating that mass on a smaller region. So by that time, it was already fairly difficult to construct reasonable alternatives. So the path was, this could be a black hole, but now we have to exclude alternative options of other configurations by going closer and closer and measuring more and more precisely. Well, how could you go from this phase onward? Well, here we are measuring basically the average of the motions. Now we would like to see actually orbital motion, direct orbital motion of individual stars. That's much more precise. But mostly in astronomy, these kinds of motions can only be detected over many hundreds of years. That's where nature came in and helped us and gave us some stars which were not supposed to be there, namely very, very close on solar system scales. And those indeed move fast enough that we can see motions. So by the early 2000s, both groups were working on 8-meter glass telescopes, the biggest telescopes we have now. And we had both equipped these telescopes with what is called adaptive optics. So instead of the speckle imaging, we are now correcting the wavefront before we detect it and make sharp imagery right away. That gives us a lot of sensitivity and high precision imaging. By 2000, Andrea's group saw the first deviations from straight motion, accelerations. So that gave us already hope that maybe we could see these accelerations for a number of stars. In particular, this one here had one of the possible solutions. You see there are 3 possible solutions, which was an orbit of only about 20 years or so. And indeed, 2 years later, both groups saw that this star, whose orbit you now see, highly elliptical orbit, approached the galactic center to about 17 light hours. Moved there at about 7,600 kilometers per second, tremendously fast, and on a distance scales of about 3 times Neptune's orbital radius. So if you put this into Kepler's laws, that gives you, again, 4 million solar masses. The same 4 million solar masses we had before, but now concentrated on the scale of only 17 light hours. Now, this is only one of the stars we followed. As you see in the movie down below, in fact, we have partial orbits for about 30, 40 stars. Yet this is the best one. So at the end of this stage, which is, a few years ago, we had ever more precise measurements of the mass. And what's more important, because of this close approach, we could exclude that the mass is any more extended than about 100 times the event horizon size. So by now, by that stage, the exclusion principle was very powerful. You could exclude all kinds of hypothetical situations, including what one would call dark astrophysical clusters, like, for instance, a conglomerate of neutron stars, 1 million neutron stars, or stellar black holes or something like this. So there's very, very little lift. 4 million solar mass black hole, and perhaps this thing here, a so-called boson star. So here we are. We have already very good evidence. Do we stop? Are we finished? No, we are not. Now we are looking at this as a laboratory. Not anymore to say, is there a compact mass? We are certain of that now. But now we want to know, A, is it really a black hole in the sense of general relativity? And is general relativity the proper theory? Also in these extreme environments which have not been tested. For that, we have to still make better measurements. So by 2004, we talked to ESO, the European Southern Observatory, and proposed to build a new instrument. A new instrument which would allow us to combine the light of all 4 8-meter telescopes into a so-called interferometric telescope, very well known from radio techniques, of over 100-meter diameter. So a 100 over 8 meters is a factor greater than 10. So actually it's more than an order of magnitude improvement in resolution. So we built this instrument we call gravity, which brings the light together from all the 4-meter telescopes. It's underneath here. You have to make all kinds of corrections, etc., which are all in tunnels underneath this device, and has been built by the European Southern Observatory, while we built this new instrument which had 3 milliarc-second resolution and a astrometric precision coming close to the event horizon scale. The star, in the meantime, was doing its orbital period and was coming back. And we were ready. So that in 2018, when the next peri occurred, we could use the interferometer now to use this high-precision tool to really look very, very closely. By the way, you can see that here you see the star in the very close to peri, and you see the black hole itself. I'll come back to this later. So the experiment, in fact, is now actually conceptually very simple. You measure directly on the sky the separation between what you think is the center of mass and the object. Here, near peri, we could see the motion every day. Previously, we had to wait for a month or two. And we had a very precise definition of the orbital parameters of this ellipse, and thereby a high precision on the mass. And now we can begin to look for effects of general relativity. And in fact, the first one is the fact that when light from the star comes to us, when it's very close to the massive black hole, it has to climb out of this potential well, which is basically leads to a redshift, to a loss of energy. And here, relative to a Newton orbit, is in fact this redshift, which we have measured, in comparison to what you would predict from general relativity, which is the blue scale. So that was already the first triumph and the first evidence that indeed GR holds, very important. This was, confirmed by the UCLA group 1 year later, and the first step. The next one is to actually show that the equivalence principle holds, and in particular, in this particular form, the positional invariance. And that we can do because in the spectra of the stars we have different atoms. Here's helium, and here's hydrogen, and here's helium. So we have different atomic clocks. And according to Einstein's theory, the results should not depend on anything but the gravitation. Shouldn't come in that there are different atomic clocks. And indeed, the results we get from the different tracers agree to within a few percent. The next effect expected is the fact that while in Newton's theory, a planet orbiting the sun on an orbit would hold its position in the plane if there's no other object nearby. But in general relativity, that's not the case. There is a precession of the orbit, which depends on the distance the star comes to the object and the mass. And so for the star S2, relative to a Newton orbit, and setting an angle equals to 0 up here at Apo, near Peri, this precession is maximum. You see basically in x-coordinate here is a kink. Or in angle, it's a change by about 11, 12 arc minutes per orbital period. So that's the prediction, and that's what we saw with gravity. Okay, here are the different measurements in x. So you see clearly this kink, and here you can see the change in angle, and indeed exactly as predicted by general relativity. So that's very, very important, because it shows us that indeed GR holds also in these extreme environments which have not yet been tested. Now, how close can we come to the center? Would it be possible to actually probe the region right around the event horizon? Well, actually, in the early 2000s, the X-ray astronomers and then we discovered variable emission in the infrared and at X-rays from the black hole itself. Continuously variable emission. And the theorists, in particular Broderick and Loeb, had proposed that what you see here are accelerated, energized electrons, which basically are formed in this hot plasma right around the black hole as the gas is orbiting, thereby forming hot spots for few tens of minutes. If so, you might be able to see the motions of these hot spots. So indeed, in 2018, on 3 occasions, the black hole got brighter than its normal state by about a factor of 100 or so. And we could see, indeed, these motions on the scale of, about 5 times the event horizon size, or 6 to 10 times the gravitational radius, with orbital periods of 40 to 50 minutes inferred from this. This means the velocities are speed of light, which is exactly what you would expect if these hotspots would move in Keplerian motion, if you like. Another thing here is that this emission is polarized. So that tells us that magnetic fields are present, and from the properties of the change of the direction of the magnetic field with time, which we can infer from these data, we find that the B fields is likely poloidal, so along the axis of the black hole and not in the orbital axis of the motion. That's surprising and probably indicates that the galactic center has a very, very strong magnetic field. This will be very important for the future to research further in order to understand this strange but highly exciting environment around the black hole. So here we are, after phase 4, Peri has happened. Now, as you see, with gravity in particular, our accuracy of measuring the mass is better than 1%. In fact, the statistical uncertainty is 0.3%. So that's a precision measurement, something which you can do not very often in astronomy. And we can penetrate now basically from the sphere of influence, where we showed the first measurements in phase 1, all the way inwards by 6 orders of magnitude close to the event horizon size. Are we done? Well, it's very likely that this object we are looking at indeed is a black hole. We don't know its spin yet, and we would have to know that in order to begin to understand whether the Kerr metric holds. And then we would have to test whether the quadrupole moment of this object fulfills what we call the No-Hair theorem. If we know that, then we would in fact have the final result that GR is indeed correct at the scale of the event horizon, which is the closest we can come. That we do not have yet, but that's where we want to go. So after these 40 years, I would say, the Galactic Center has been extremely helpful to astronomy and to physics. 2 groups have used this to push ever further, and many questions remain or go beyond what we have now but we now have evidence indeed that these objects, which were theoretically discussed by Roger Penrose and others, actually are realized in nature. Thank you very much.
It is my great pleasure to introduce our third 2020 Nobel laureate in physics, Professor Andrea Ghez. The title of her talk is From the Possibility to the Certainty of a Supermassive Black Hole. Andrea Ghez earned her PhD in physics in 1992 from the California Institute of Technology. The following years, she held a Hubble postdoctoral research fellowship at the University of Arizona. Professor Ghez has been at the University of California in Los Angeles since 1994 and became full professor in the year 2000. In 2014, she became the head of the Galactic Center Orbits Initiative at UCLA. Andrea Ghez has been pushing the frontiers of imaging at near-infrared wavelengths using the Keck telescopes in Hawaii. Her masterful use of laser-guided adaptive optics allowed her to make detailed mapping of the orbital motions of resolved stars close to the galactic center. The ultimate goal was to uncover the nature of the supermassive object lurking in the innermost part of the Milky Way. Professor Ghez, we are excited to hear about your fascinating discovery.
I'm so grateful to have the opportunity to speak in this forum. Before I begin, I'd like to dedicate this talk to two people who were very important in my development as a scientist, but are no longer with us. First, my father, Gilbert Ghez, who taught me to be curious about the world of numbers and to find their delight. And second, my PhD advisor, Gary Neugebauer, who taught me the importance of paying attention to data above all else. The work that is being recognized is a 25-year-long project that I began when I first started my faculty position at UCLA. UCLA was my dream job because it gave me access to the newly constructed Keck telescopes, which are the largest telescopes in the world. And I was interested in developing new ways of using this telescope to study black holes. I like to begin my lectures with the question, how do you observe something you can't see? This is an essential question if you want to find and study black holes, because black holes are objects whose pull of gravity is so intense that nothing can escape them, not even light. The story that I would like to tell you today is how we've been able to find a supermassive black hole at the center of our own galaxy, and this has provided us with the best evidence yet that these exotic objects really do exist, but it's also provided us with a wonderful laboratory for studying the fundamental physics of black holes, and in particular, how black holes warp space-time, and what role black holes play in the formation and evolution of galaxies. While the black holes are relatively exotic objects and require pretty exotic physics to properly describe them, the way I want you to think of a black hole today is an object whose mass is confined to zero volume. So despite the fact that I'm going to talk about objects that are supermassive, and I'll get back to what that means, they have no finite size. So what does this mean? This means that if we think about density, which is mass divided by volume, density goes to infinity. And in physics, anytime you have a number going to infinity, this is known as a singularity, which is equivalent to a giant red arrow that says you don't have your description of the physical world quite right here. So in fact, this is what makes black holes so interesting, because it points the way forward to understanding a deeper way of thinking about physics. Today, we don't know how to make the world of general relativity, which describes gravity near highly gravitating objects. So that's what Einstein is so famous for, work together with the study of quantum mechanics, which is the study of things that are very small. And black holes are both. They have tremendous gravity and they're infinitesimally small. So when we understand what a black hole is, we'll be able to presumably make these two fields work together. But in the meantime, fortunately, there is an abstract size that we can think about that's quite important to the studies of black holes. And this is known as the Schwarzschild radius. And this is the size that if you can compress an object down to its Schwarzschild radius, and in fact, every object has a Schwarzschild radius, gravity will overcome all other known forces, forcing the object to become the infinitesimally small object of a black hole. So if we think about the Earth, and we could figure out how to squeeze it down to the size of a sugar cube, it would become a black hole. Now, fortunately, the Schwarzschild radius is actually quite simple to figure out. It just scales with mass. So if we were to look at a more massive object like the sun and scale it down to UCLA's campus, I couldn't help but put UCLA in there, it would become a black hole. So this notion is important because it not only defines what a black hole is, but it gives us a way of demonstrating or proving that a black hole exists. We need to show that there's some mass confined to at least within its Schwarzschild radius to claim a black hole. So in astrophysics, there are two kinds of black holes that we talk about. And in fact, they're a wonderful example of the interplay, the different ways that science proceeds. So in the first kind that I'm going to call the ordinary mass black holes, as if there could be such a thing as an ordinary black hole, are black holes that were thought from theoretical work that thought about what would happen at the end of a very massive star's life. So a star that starts off with more than 30 times the mass of the sun, it's thought at the end of its life, it's going to become a supernova. And what we're seeing here is that the outer layers explode off into interstellar space, and all sorts of exciting and really important things happen here. But for the point of view of this talk, what's interesting is what happens at the middle. In the middle, gravity overcomes all other known forces and is expected to become a black hole that has roughly 10 times the mass of the sun. So this was identified from theory and then subsequently verified by observations. So we have wonderful evidence today of the existence of these stellar mass black holes. Now, the story of the supermassive black holes is quite different. And by supermassive, I mean 1 million to 1 billion times the mass of the sun. This is a story which is led observationally. And observations of galaxies, and in this picture, almost every object in the galaxy is a galaxy. Only one object in here is actually a star within our own galaxy. So let's focus on the top left corner here. This is a galaxy. So this is a very different scale than the last picture that we were looking at. We were looking at a single star. Here we're looking at a galaxy that has 100 billion stars. So it's a really different scale. And there's actually nothing in this picture that suggests the existence of a supermassive black hole. Because what this picture is that taken at optical wavelengths, which is what your eye detects. So you're sensitive mostly to starlight. So the idea of supermassive black holes residing at the heart of these galaxies came from radio pictures. Radio pictures of a tiny class of galaxies known as active galactic nuclei. And the name says it all. We think the nuclei, or the center, is very active of the galaxy. And so this is a very different picture. So at radio wavelengths, so somewhat akin to where your cell phone works. And you no longer see the starlight, but rather you see these jets of emission emanating out from the center. The whole galaxy is roughly in a modest scale at the center. So these very energetic jets, combined with the fact that the emission from the center of the center of the galaxy, looks unlike anything emitted by stars or gas, led people to suggest that perhaps it's a supermassive black hole that's driving all this energetic phenomena. And in particular, it's a black hole that is dining or feasting or accreting a lot of material from its surrounding. So these, you could say, are like galaxies that are having a Thanksgiving feast. Now, this led people to think about the possibility that perhaps all galaxies harbor supermassive black holes at their centers, but these are rather stealth black holes, or rather black holes on a diet, because they don't have the material around them to light them up. Because remember, black holes themselves don't emit any emission. And in fact, this galaxy, which is the one we were zooming in the galaxy picture, looks very much like what our galaxy would look like if we could get outside it and look back. In fact, our solar system is roughly halfway out. So galaxies in general are flattened disk-like structures. So if we're going to ask this question of, do all galaxies harbor supermassive black holes? Or really, more profoundly, do these supermassive black holes exist? Our galaxy is simply the best place to look because it's the closest example of the center of a galaxy we'll ever have to study. It's 100 times closer than the next closest galaxy. Now, so the pro in studying our own galaxy is that it's close, the center of our own galaxy. The con, because in life, usually every time you get a pro, you get a con, is that we're in this flattened disk-like structure. We're about halfway out, and we're looking through the galaxy to the center. So this is a picture of our own galaxy. If you could get out to a dark site, this is actually taken from the side of Mauna Kea. And what you see is the galaxy, the plane of the galaxy. It's lit up with stars, so you see it as a band of white light, or that's why it gets its name, the Milky Way. But in the middle of it, you see a dark lane, and that dark lane is dust. And dust is like smog in LA. It's very good at absorbing optical light. So we can't see through the center of the galaxy, through the galaxy at optical light. So if we think about the ability of light to penetrate from the center of the galaxy to us, optical light, what our eye detects, only 1 out of every 10 billion photons or light packets makes it from the center of the galaxy to us. In contrast, if we go just slightly longward of what your eye detects to the infrared, which is where your TV remote control works, 1 out of every 10 photons makes it to us. So in fact, you can see or perceive what's happening at the center of the galaxy if you go to infrared wavelengths. So a key to this work has actually been the rapid development of infrared technology over the last 30 years. So if we want to prove most directly the existence of a supermassive black hole at the center of our galaxy, the most direct way that we can do this is by watching how stars move. So stars move under the influence of gravity of whatever's inside their orbit. So their orbit, by measuring how fast it goes around and the size of the orbit, you can figure out how much mass is inside the orbit. This is just due to gravity. It's for the same reason that planets orbit the sun. So these stars are orbiting the black hole or whatever is inside its orbit for the very same reason. So if you want to show that there's a lot of mass confined to a very small volume, it's the stars that are as close to the heart of the galaxy that are the keys. So in a sense, we're inward bound in order to carry out this experiment. And this actually tells you very much why I was so interested in getting access to the Keck telescopes. So as I said before, the Keck telescopes are the largest telescopes in the world. And we characterize telescopes by the width, or the diameter rather, of the mirror, the collecting element. And these telescopes, there are 2 of them, each one has a mirror of 10 meters. So to give you a sense of scale, this is equivalent to the width of a tennis court. Now, the campaign promise of large telescopes are twofold. One is that with a large telescope, you should be able to see things that are very faint. You can think of it as a light bucket. The larger your telescope aperture is, the more light that you can collect in a given amount of time. So for a typical astronomer, you're interested in seeing things that are faint, which is equivalent to things far away. And this is effectively a history lesson in many cases, because it takes light a finite amount of time to travel to us. Now, what I'm interested in is actually the second campaign promise, which is the idea that large telescopes, the larger the telescope, the finer the detail that you can see. So this is called angular resolution. And the analogy I like to make here is it's like the painting technique of pointillism. And the closer you get to the painting, the better your ability to resolve those individual dots. So that as you go closer to the painting, you're improving the angular scale of those dots. Now in astronomy, the equivalent is by getting a bigger telescope, you should be able to see smaller structures out in space. Now, the challenge, or why this second campaign promise has been so difficult to achieve, is the Earth's atmosphere. The Earth's atmosphere is great for us. It allows us to survive here on Earth, but it is a total headache for astrophysicists because it distorts our images of astronomical objects. So this is an animation of data that we took early on of the center of the galaxy. And there are 5 bright stars that are seen or in this picture. And if there were no atmosphere, the structure of each star would be equivalent to the smallest structure that you're seeing here, and rock solid, as opposed to something that looks more akin to a bug splat pattern. And it's actually rather profound if you think about this, because the light that we're collecting here came from the center of the galaxy. It actually took this light 26,000 years to travel from the center of the galaxy to us, and it's in the last 30 microseconds that it hits the top of our atmosphere and becomes completely distorted. So I'm interested in ways of overcoming this, this problem, because otherwise you can't get to the promised resolution of a telescope. And over the last 25 years, there's been a tremendous revolution in the ways that we've done this. So this is an experiment that, as you'll see in a moment, is benefited by time, just the duration of how long you've been making the measurements, but it's also benefited tremendously from the advancements in technology, which has improved our ability to make these measurements. In the beginning, we used something fairly straightforward and simple, which required lots of computational power, but very little hardware. And then in the last 10 years, we've gone on to a much more sophisticated hardware-based solution. And in fact, this is nicely connected to the military, because it turns out the military cares about seeing both up and down through the atmosphere. So they were developing techniques as well. So in the early 90s, there was a huge leap forward in our ability to correct for the distorting effects of the Earth's atmosphere. This new technique of adaptive optics, the way I like to describe adaptive optics, or even the problem of the atmosphere, you can think of the problem of the atmosphere in 2 ways. One is as a river that's turbulent and moving by you quickly. And the equivalent of seeing our astronomical objects is like seeing a pebble at the bottom of the river. And that moving river makes that object look distorted because of the turbulence in the river. So our job is to take that turbulence out of our, or the distortion that's caused by the turbulence out. So another way to think about this is like a circus funhouse mirror that's warped and makes, if you only look at one of them, makes you look distorted. So the goal of adaptive optics is to put in a mirror that has the exact opposite shape, or the conjugate shape, to take out the distorting effects of the Earth's atmosphere and make you look flat again. And of course, you have to do this at really rapid speeds to keep up with turbulence in the Earth's atmosphere. So typically, this is a system that's running at about 1,000 times a second. Now, before we were looking at a little inset screen, or an inset box to what was happening at the center of the galaxy. So we're only looking at that little central box to see what happens to the stars there. Now, we actually have a much bigger field of view, and we're tracking thousands and thousands of stars. But if we zoom into this scale, you can see what's going on. And at this point, it's probably helpful to think back to the beginning of this experiment, which was the early 1990s, to realize the skepticism with which people held this experiment. Because in fact, the first time we put in this experiment, proposed to use the telescope, it was turned down. It was turned down because people didn't believe our techniques, those early techniques, would work. And even if they did, we wouldn't see stars, and even if they did, we wouldn't see their motion. So I have to say, this is one of my favorite movies to watch. So on the left is what we did for the first 10 years. That was the computationally intensive but hardware simple approach. It didn't give us much. It gave us an image at a single wavelength, but it told us that there were stars there. And you can probably find my favorite star in the galaxy. Its name is S02. It probably needs a better name, but for the moment, it's a name that actually helps us identify where in the field it is. Now, the next 10 years of adaptive optics made the observations much more powerful. Now we can take measurements, images that are much deeper, so you can see far more stars. You can position these stars far more accurately. And you can take images at a number of different wavelengths, and you can take spectra for the first time. And those spectra are important for a number of reasons. One is that for the first time you get to measure the motion along your line of sight. So this movie shows you how things are moving in the plane of the sky, but you're missing the third dimension. So spectroscopy allows you to figure out how things are moving along the line of sight, and for the first time, actually allows you to explore the astrophysics of these objects. In other words, to ask, well, what kind of stars are we looking at? And I'll return to that in a moment. Now, the next animation I'm going to show you is a fourth of the real estate. I mean, this is a ridiculously small scale. If you recall back to the original animation, without any of these techniques, it's one blurry image over the scale of this image. In other words, without adaptive optics or speckle imaging, your resolution would be the size of this box. So we're going down to a fourth of the scale, and that's necessary because things are moving so fast. And I never get tired of looking at this animation either. It really describes, so this is no longer the direct data. The last images were real data. There was nothing enhanced about them. It was just the data that we get shown. Now this is an animation that shows how the brightest stars that we're measuring, not all of them, are moving over the last 25 years. So this is definitely an experiment that requires a tremendous amount of patience. In this animation, when a star is detected in an image, it's trailed by a dashed line. So you'll see that stars appear, and they're not appearing because they're getting brighter, but rather that your sensitivity, your adaptive optics has allowed us to see stars that the speckle imaging experiment didn't allow us to measure. And then when it's trailed with a solid line, we finally have the instrumentation and methodology that's allowing us to measure the spectroscopy of that particular star. So you can see that there's a time evolution in our ability to get spectra as well. Okay, so this is just getting better with time. The other thing that I'd like to take a pause to just acknowledge is that when these experiments, both those done by my group and those done by the Max Planck group, no one envisioned orbits. We were just thinking about velocities. So remember that even the idea of measuring speeds, how fast individual stars are moving on the plane of the sky, was already a challenging enough concept back in the early 90s. So the idea there was just that stars closer to the center would be moving faster on average. So you're just setting out to measure little arcs, so little line segments. So that was the first phase of the experiment, and yet people in the late 90s, by the time these experiments were being published, were questioning and suggesting that there could be all sorts of other things pushing these stars around, so we kept going. And the next thing you can kind of see from this animation is that things are going to deviate from a straight line. So then in about 2000, you could measure accelerations, and the minute you get accelerations, you understand how exciting this project is going to be, because you can foresee at that point that the orbital periods are going to be shorter than a human lifetime. And here again, just consider that it takes the solar system 200 million years to get around the center of the galaxy, and here we're talking about things that are happening on a decade time scale. So my favorite star there is going around every 16 years. And what is that star? I mean, now we have the most direct. So the early velocity ideas was an indirect sort of statistical approach, so sort of phase one, accelerations were phase two, and then the orbits were really the important phase three. With phase three, you see an orbit that's going around every 16 years. And what does that tell us? Well, before we started this experiment, we knew that there was 4 million times the mass of the sun inside a region that's depicted here with a circle. And at this point, you're well outside the Schwarzschild radius. But what this experiment has done is to show that, in fact, there's 4 million times the mass of the sun inside a volume that's 10 million times smaller. And that volume corresponds to the scale of the solar system. So there are a couple of things to point out here. If we think about our own solar system, there's one sun worth of material there, effectively. Now we have the same region that you have 4 million times the mass of the sun crammed into that region. And this has actually increased the evidence for a supermassive black hole by a factor of 10 million. I mean, think about anything that you could move forward or increase that you'd like more of. In this case, this has been a dramatic increase, which has really moved us from the possibility of a supermassive black hole to a certainty that there's a supermassive black hole at the center of our galaxy. And not only at the center of our galaxy, but really of any other galaxy in the universe. All right, so this is really what is being recognized with this prize. But there's so much more that's happened with this work which has really given us an ability to see the center of the galaxy in a way that really hasn't been possible before. So I want to just very briefly touch upon two things. One is our ability to understand the role that supermassive black holes play in the formation and evolution of galaxies. When the work was first being announced in these various stages, the thinking about this question was very different. It was really the chicken or the egg. Which came first, the galaxy or the black hole? So this is like the chicken or the egg problem. And in fact, we had ideas for how to get either one of these scenarios to work. But today, what we recognize as more and more candidate supermassive black holes are emerging, that that's just the wrong framework. And in fact, the mass of the black hole seems to correlate with the mass of the central part of the galaxy, and called the bulge. And the scale of these two objects are so vastly different that we recognize today that whatever formed one had to result in the formation in the other, and that over time there has to be a feedback mechanism between the two. Now, one of my favorite aspects of this project is that it has allowed us not only to address the question that we set out to address, but it has raised more questions that it has answered. And this animation just touches upon a few. We anticipate, and in fact it was an early argument against the existence of a supermassive black hole, that there should be no young stars. And there were some young stars hanging around the outside of that really big circle before, which was one of the arguments against a supermassive black hole at the center of our own galaxy. And today we recognize that there is a supermassive black hole, and the stars that we were tracking right at the center are young. Okay, so I like to call that problem the paradox of youth. So we have a lot to think about. And as you can see in this, actually what I should say is in this animation, the young stars are the aqua blue. So they are actually the most dominant part of the population that we can see is the young stars, which we predict should not be there. And in this animation, as it pulls back, you can see a plane, which is providing us with a very important hint as to how those stars arrived to be where they are. We actually think that there was an episode of star formation, which probably made our galaxy look a lot like those active galactic nuclei that I mentioned to begin with in our galaxy's history. But that was millions of years ago. The other prediction is that there should be lots of old stars. Old stars have lots of time to congregate or settle into the middle, to congregate around the most massive object in the system, and that's the black hole. And the old stars are the orange things, and in fact, there's a dearth of old stars. So that's sort of paradox number two. Where are the old stars? And then the third thing that I find the most interesting is the thing that we didn't even think to make predictions for, are these objects that are being tidally torn apart as they go through closest approach to the black hole. These are objects that we can see evolve in their characteristics as they approach the black hole and then emerge out the other side. And today, we think that these are stars that have been driven to merge, so pairs of stars that have been driven to merge by the supermassive black hole. And we think this actually might illuminate important processes that connect what's happening at the center of the galaxy with the gravitational wave detections that have been recently observed with LIGO. Now, the last but not least, I want to turn my attention to using the center of the galaxy as a test or a laboratory for understanding how gravity works in this extreme environment. So we know that supermassive black holes ultimately represent the breakdown of our understanding of how gravity works, because we don't know how to make quantum mechanics and general relativity work together. And the depiction that you often see in science museums is to flatten out 3 dimensions of space into 2, and then to use the 3rd dimension as to depict time. So as you approach a black hole, you get this mixture of space and time, which is one of the predictions of relativity. And these orbits of stars are providing us with the first direct tests of how gravity works near a supermassive black hole. And there are two tests that are now possible. One, you can look at how photons are affected by their climbing out of the gravitational potential well. They have to give up some energy. And in fact, as this star goes through closest approach, SO2, that was actually seen. So this effect is actually best seen at closest approach. So that was seen in 2018, and I'm going to call that phase number 4. And then the next thing is the precession of the periapse, which is how the object itself moves through space and time. And this is best seen at apoapse. I should say for both of these, you need to see the orbit go all the way around once. In other words, in order to get a seat at the table for doing these next two projects, you have to have the measurements for the first complete orbit, which is 16 years. So there's a lot of patience to get to this next phase, but the signatures are emerging. Now, before I conclude, I'd like to acknowledge that all of this work has been done in collaboration with a number of people, and in particular with my long-term collaborators, Eric Becklin and Mark Morris, who are shown on the left, and also included in this picture is my first graduate student, Beth Klein. So this started as a small project with with 3 collaborators. Today, it's a much larger team. Today, we're a collaboration of 30 people. And along the way, over 25 years, we've had 4 or 5 generations of students who have been trained to do all sorts of wonderful things. They've gone on to academia, to industry, to the financial world, to all sorts of amazing jobs that this kind of training opens the door to. All of this work has been done with support from a large number of organizations over the last 25 years. I in particular want to acknowledge the backbone of the support, which comes from UCLA and the National Science Foundation. And then along the way, we've been so fortunate to be supported by those who support early faculty work with the Sloan Foundation, the Packard Foundation, and the MacArthur Foundation. And then more recently, we've been supported by the Keck Foundation, the Moore Foundation, and the Heising-Simons Foundation. And last but not least, I'd like to recognize the role of the Galactic Centers Group's Star Society group, in particular the chair of our board, Arthur Levine, and his wife, Lauren Leichman, who have been just amazing supporters of this work for the last few years. So let me conclude with, if nothing else, I hope I've convinced you that we have remarkable evidence for the existence of a supermassive black hole. This evidence has increased our understanding of the presence of a black hole by a factor of 10 million, which has moved the idea of black holes from a possibility to a certainty, and the revolution in technology that has come with this has opened more questions than answers. So there's more work to be done, and thank you for your attention.